Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Okay, so this is week number 14. Okay, so I would like to continue moment distribution method beam analysis. So I will continue beam with support settlement effect. Okay, but before that, I would like to revise back to what we have learned last week. Okay, so under moment distribution method, we have to analyze two types of structure. One is beam, another one is frame. So I actually cover beam analysis only. Okay, in moment distribution method, there are some important terms that you need to understand, especially the member stiffness, how from the member stiffness we calculate the distribution factor, because distribution factor is the one that we use in the table to distribute moment. And then we have to understand also the fixed end moment, fixed end moment or fixed end reaction. Okay, fixed end moment. So fixed end moment is actually based on two conditions. One is due to external loading and another one is due to delta. So for beam, delta is for support settlement effect. And for frame, delta normally cater sideway frame analysis. Okay, so there are two values of carryover factor. Okay, considering far end conditions. So all this I have actually explained in my previous lecture on MDM beam last week. Okay, so the coverage, as I mentioned, so beam has we have to consider analysis without support settlement and with support settlement. So how to differentiate it? We differentiate it by using the FEM formula. Okay. Okay, the sign convention we use for moment distribution method. Okay, since we use Hibbeler as our main reference, main textbook, so it is clockwise positive. It is clockwise moment that act on the member are considered positive. So otherwise, okay, counterclockwise moment are negative. This is clockwise member that act on member. So it is actually differ if we compare to joint moment, because the moment that we analyze, the moment that we distribute is actually joint moment, not member and moment. Okay, so we have to understand fixed end moment, because fixed end moment is the first member and moment in the table. Fixed end moment is the first member and moment in the table. And always remember, the moment that we distribute in the table is not member and moment but joint moment. And joint moment is always opposite with member and moment. So that is why during the distribution process, when we want to distribute, what we normally do is we will change the moment sign. So why we need to do that? Because the moment that we distribute is joint moment, which is opposite with member and moment. Okay. So this formula of fixed end moment we can find at the back page of the textbook. Okay. So actually, for fixed end moment, there are two types. Considering far end condition, we have far end fixed and far end roller or pin. Okay. However, we can actually solve all types of question or types of problem by considering both end fixed. Both and fixed means that we consider far and fixed only. Okay. And the formula, okay, the last formula, number 5, number 5 formula is it is actually the fixed end moment considering delta. Means that for beam with settlement, beam with support settlement, so we have to use the formula. There is only one formula considering for both and fixed or for and fixed, it is 6 EI delta over L squared. Okay, let's look at to the example. Okay, this is the example that we have actually discussed last week. So we revised this back before we move to example considering support settlement. Okay, always remember that the joint the output, okay, the goal, the objective in analyzing a beam or frame using moment distribution method. Okay, we actually calculating member and moment or internal moment or bending moment. It is member and moment. Member and moment. So this question is actually taken based on example 12.1 under textbook. Okay, the question is determine the internal moments. Internal moment. It is equivalent to member and moment. It is equivalent to bending moment in the beam. Okay. So by looking at this beam, there are three elements or three members, member AB, member BC, and member CD. Okay, so there are, okay, NA is fixed and D is fixed. Okay, I have actually explained to you in my previous lecture that far end condition are normally referring to the first and the last point in the structure, because internal support like C and like B and C are always assumed as fixed. Internal assumed as fixed. That is why the stiffness factor for BC, for member BC, we will use 4 EI over L because internal are fixed. Okay, so AB for member AB, K member stiffness for member AB, member stiffness for member CD. Since A is fixed, D also fixed. So all members in this question, in this example, we use 4 EI over L, and 4 EI over L is for far and fixed formula. Okay, so we use far and fixed here, far and fixed. Okay, it is 4 EI over L. We calculate K, okay, for each members, KAB, KBC, and KCD, because stiffness is 4 element. We have 3 members or we have 3 element, so we have 3 value of stiffness factor. And from the stiffness factor, we have to calculate distribution factor, and distribution factor equal to K divided by total K of member stiffness divided by joint stiffness. Okay, so I will not detail it again, okay, because I believe everyone who joined my class by session last week, so you should understand about how to calculate distribution factor. And this is very actually quite straightforward. And for those who come from diploma, okay, you have gone through all this. This is just the second time you learn moment distribution method. Okay, so the next step after we have determined K, we determine distribution factor is the fixed end moment itself. Fixed end moment, as I mentioned, is the first member and moment in the table. The first member and moment in the table. And anyway, we actually distribute joint moment, and joint moment is opposite with member and moment. And always remember that fixed end moment, the sign that we put in the diagram, when we calculate fixed end moment, okay, this is actually based on the behavior. So fixed end moment is behavior. So this direction we get, okay, we get the direction, okay, in the diagram is because of the behavior of the beam due to the loading. Okay, due to the loading after W or P, okay, is subjected on top of it. So it is behavior. Okay, so that is why we get 1 negative, 1 positive. because what we get is the band beam. Okay, the band beam, and the fixed end moment is actually the fixed end moment will push both end so that the band beam will move back to its original position. So that the band beam will move back to its original position, means straight position. That is why we have to apply moment in those direction. So from the sign convention that we have set for moment distribution method, we will get FEM for AB as negative and FEM for BA, okay, BA as positive. Okay, so we do the same for member CD. For member CD, this is C and D actually. C and D. So we get one negative, one positive, because the behavior we compare with sign convention. The behavior we compare with sign convention. So that is why we get one negative, one positive. So all these FEM values we have to put into the table. We have to put into the table. So we get okay. So in the table we must have table. We list all the members, all the member n, not all the members, all member n, because one member has 2n. One member has 2n. Okay, so 3 members, we have 6n. So 6n member and 6 member n. So we have AB, BA, BC, CB, and CD. So there are 6, and this 6 will represent number of member and moment that we need to calculate at the end of this table analysis. Okay, so due to that, we have to have 6 degree distribution factor as well. 6 distribution factor. So we get distribution factor from stiffness factor, and the special is for n fixed and n fixed A and D, and fixed A and D, distribution factor equal to 0. Distribution factor for n fixed A and D equal to 0. So the rest we have to calculate. So we get BC 0.5, 0.5. We get CB, CD 0.4, 0.6. So always remember this one, okay, is distribution factor at joint. Distribution factor at joint equal to 1. Distribution factor at joint equal to 1, except n fixed. This is distribution factor equal to 0 because of fixed n. Distribution factor equal to 0 because of fixed n. Other than that, total distribution factor at joint equal to 1. Okay, so we put the fixed end moment. That we have just calculated, and then we start distribute moment. Okay, so I will not explain detail again for how we distribute moment. Okay, please refer back to the previous video. So we do the distribution process in the table. It is distribution and then carry over, distribution, carry over, distribution, carry over. We repeat the process again and again until last distribution. And we must end at distribution. We cannot end the process at carry over. We must end the process at distribution, and we have to total all the moment value. Start from fixed end moment, because fixed end moment is the first member and moment in the table. Okay, we total, then we get member and moment. We get internal moment. internal moment means that bending moment. So the moment that we get directly from the table is actually the value in the bending moment diagram. So from the value, we can straight away draw the bending moment diagram. Okay. So this is example 2. Example 2. Okay, example 2 ni. Example 2 is actually two beam span. Two beam span, member AB and member CD only. Normally, when we have two members, the process, the distribution process is very short. Okay. Anyway, this is the example shown how we analyze n for n fixed at A and for n roller at C. The process will be the same. Okay, except the formula to calculate K for member BC is not 4 EI over L, but 3 EI over L, because 3 EI over L is the formula to calculate member stiffness for n roller. So the process will be the same. Okay, and then what we get in the table is like this. Distribution factor at A, because A is fixed. Because A is fixed, it is equal to 0. A is fixed. Okay, other than that, at B and at C, distribution factor must equal to 1. Distribution factor at C must equal to 1. B, at joint B, we have to divide into BA and BC. That is why we get two value, BA and BC, and the total BA plus BC, we will get 1. We will get 1, representing distribution factor at joint equal to 1, except distribution factor for fixed N. Okay? For fixed N. And we put the moment, calculated, the fixed end moment calculated based on this diagram. Based on this diagram is referring to the fixed end moment for column, fixed end moment considering for n roller. Fixed end moment considering for n roller. That is why we only get one value for moment MBC, because there is no moment value at roller CB. Okay, so the process is very short, so we get like this. Okay, so this process, this table, the moment in the table, we end at carryover because next distribution, all value will be 0. All value will be 0. Anyway, always remember, when we have example, like previous example, we have 3 span and more, we have to choose to stop at distribution. Choose to stop at distribution. Okay, because if we stop at carryover, we cannot balance the value. Okay, anyway, in this example, because there is no moment to distribute, that is why we can see that the last value is carryover here. Okay. And then the moment that we get, the n moment that we get from the table, we can straight away draw the diagram, the bending moment diagram, because that's the same. Okay, so this is another another question, indeterminate beam that we can solve using moment distribution method. Okay, moment distribution method, there are 3 span AB, BC, and CD. Okay, so this one you have to try on your own as your self-learning exercise. Okay, and then you can check the answer. Okay, same goes to exercise number 1. Okay, so now I want to move to this exercise number 2, because this one is example of beam analysis, indeterminate beam analysis, considering support settlement. Considering support settlement. You can see from the question, that the support B and C settle. Support B and C settle by 8 mm and 4 mm respectively. B and C settle by 8 mm and 4 mm respectively. So this is only 2-span beam. So for 2-span beam, the process will be very short. Okay. Anyway, I want to refresh back. Actually, I have also discussed about the concept of fixed end moment due to delta, due to support settlement last week. So before we analyze this together, so I want to refresh back the concept of fixed end moment due to support settlement. Okay, so basically, okay, this is actually the formula. Okay, the formula, beam with support settlement, original. Okay, always remember, for beam, original position is horizontal. Beam original position is horizontal. Original position of beam is horizontal. This is delta. Original. So if this is A, this is B. So original beam is horizontal. Okay. And then we measure the delta, which is perpendicular with member. We measure delta which is perpendicular with member. So it is easier if we complete this as one triangular. Okay, complete this as one triangular. Okay, so this is the 90-degree, so that we get full triangular. So length, this is the length. Okay, span AB. Okay, the vertical height is actually the vertical displacement, and this delta occur in beam normally due to support settlement. And always remember, FEM is actually behavior. FEM is behavior. So always remember that a beam is a horizontal member. And moment, fixed end moment, will push back not the bend beam. The bend beam is due to loading. Okay, the fixed end moment. Okay, the fixed end moment acting at A and B. Okay, it is actually push back the beam, the new position of beam to its original position. Original is horizontal. So focus on please focus on the beam after settle. Beam after settle is this. Beam after settlement. Okay. If B is settled, beam after settlement is going to be like this. Okay, so we have to apply moment at both end, A and B. So how to do that? Okay, we will apply moment that act to counter back the end, and A and B, so that the beam will move back to its original position. So we have to apply moment in this direction. We have to apply moment due to the behavior. due to this behavior, we have to apply moment counterclockwise, so that the moment will push back the beam to its original position, which is straight position, which is horizontal position. This is when B is settled. And always remember, when we want to analyze FEM due to support settlement due to delta, so if both ends are fixed, the moment will be negative. So from this we get, okay, if you want to calculate the value for this one, so let's say this is 6 meter, for example. Okay, delta B is given as 30 mm downward, So we get two FEM AB, FEM BA, both has same sign. Okay, this is FEM AB, and this one is FEM BA. Both have same sign. So how to calculate this? So it is FEM AB equal to FEM BA equal to, so we put negative because we know that we will get negative value. We know that we must get negative value representing the moment direction. Okay, the moment direction to push back the beam to its original position. It must be negative because of the behavior. So it is 6 EI, delta is 30. Okay, delta is 30. This is 0.03 divided by L. L is 6 square. So we get negative value. So that is how we calculate FEM due to support settlement. So actually, so we get negative, right? We should get negative value here. Okay, we should get negative value. Because of the behavior. So actually, by looking at the diagram, we can have one conclusion about the behavior and the sign, the FEM sign. So what we can conclude is like this. Okay, between original position and new position of the beam. New position mean beam after settle. Same goes to frame after side sway. Same behavior. Okay, so mark the angle from original. Beam. The angle. It is called as chord rotation. Mark the angle. The angle is positive. Same if we also mark here. Because horizontal is always the reference line. We measure the angle from original. Okay, what we can conclude is between angle and FEM, what we can conclude is angle positive, angle clockwise, FEM counterclockwise. It is opposite. Okay, these two between angle, chord rotation, and FEM, okay, must be opposite condition. Okay, these two. Opposite. Opposite condition. Okay, opposite condition. So, whenever, for example, A is settled. For example, A is settled. So, when A is settled, it is like this. Okay, where is the triangular? Complete the triangular. Complete the triangular. Okay, complete the triangular. Mark the angle and chord rotation. It is chord rotation. Angle. So we can conclude angle counterclockwise. Angle is counterclockwise. So FEM is clockwise. Okay. So if this one is 6 meter and delta is 35, for example. So FEM, let's say this is AB. So we get FEM AB equal to FEM BA equal to FEM clockwise. FEM clockwise. So what we get is positive. It is positive 6 EI delta divided by L6 square. And the answer must be positive, representing behavior. Because when we have this, when we want to push this beam to straight position, to horizontal position, the moment that we apply should be in this direction. Positive. Okay. So this is how we analyze FEM due to settlement, due to delta. This is for beam. Beam is a horizontal member. Okay, so now we will, okay, we go back to exercise given here. Exercise given here. Okay, so there are two span. So two span, as I mentioned, if we have two span, the distribution process will be very short. Okay, if we have three span, we will have more cycle, more distribution cycle. Okay, we have to analyze this beam using moment distribution method. Support B and C settle. So always remember, when we have support settlement, we have to mark, identify the triangular, and we have to mark the angle, the chord rotation. Okay, so that is that's the process. Okay, but we don't have to this beam has external loading, and we have to combine between FEM due to external loading and FEM due to support settlement. Okay, we have two types. We have FEM, which come from external loading and come from support settlement. So in order to analyze this beam, we can actually do it separately. One table for FEM due to due to loading, and another table is for FEM due to support settlement. Anyway, we can also combine FEM and solve the end moment in one table, because FEM due to loading, we can calculate directly because the loading is all given. and FEM due to support settlement also, we can calculate it directly because settlement is known value, not unknown value. Okay, settlement is known value, so we can calculate the value of FEM directly and we can plus with FEM due to loading. But these things cannot, we cannot apply this in frame because frame, the delta in frame, the side sway value, we do not know the value. Okay, but in beam, since we know the delta, so we can solve using one table. We can solve using two table if we want, and we can also solve using one table. One table means we combine FEM. We combine FEM. Okay. So sketch shear force diagram and bending moment diagram. Okay, so AB 4 meter, BC 6 meter, 240 subjected at the center of member AB, and 40 kilonewton per meter is loaded along member BC. Along member BC, and length for member BC is 6 meter. Okay, A is for and A is fixed for and fixed. C is roller, for and roller. So for and roller. So for member AB, we use 4 EI, 4K, 4 EI over 4. And for member BC, we use 3 EI, since EI is constant, okay. 3 EI over 6. Okay, for distribution factor, distribution factor for NA, distribution factor equal to 0. For NC, distribution factor is equal to 1. And we have two values of K, two value of distribution factor, DFBA and DFBC. DFBA and DFBC we get from the stiffness factor. The stiffness factor, it is, okay, it is 1, 4 divided by 4, 1 divided by 1.5. It is 0.667. So here is 0.667 and minus 1, 0.333. Okay, this is distribution factor. Distribution factor. Okay, so we will calculate FEM. FEM for member AB. FEM for member AB. It is 240 and 4. This is AB, 240, 4 meter. Okay, moment acting in this direction. So it is FEM for AB. This is negative PL over 8. 240 times 4 divided by 8. So this will equal to negative 120 kilonewton meter. So we get FEM for BA positive 120 kilonewton meter. Okay, and then for member 40 and 6. Okay, for member BC, okay, for member BC, this is 46 meter. So as I mentioned, even though B and C is roller, we can still analyze structure, analyze fixed end moment by assuming both end are fixed, and we will see together after this how to analyze this by considering Okay, by assuming both ends are fixed. So we just refer to the first column of the fixed end moment formula, considering both ends fixed. So we don't need to use the second column of the formula for fixed end moment, considering end and pin or rolling. Okay, so this one, so it is WL squared over 12 because we assume both ends are fixed. It is W40, L is 6 square over 12. So it is 120 as well. So this is 120, 120. Okay, this is 120, 120. This is 120, 120. Okay, so if both ends are fixed, so we have to have moment at both ends. So it is BC, BC negative 120 kilonewton meter, and FEM CB is positive 120 kilonewton meter. Okay, so all these are the fixed end moment considering external loadings. Considering external loadings. Okay, now we want to move to the second part where we have to consider support settlement. Support settlement. Okay, fixed end moment considering support settlement. Okay, so settlement occur. Okay, based on the question, settlement occur at B and C, 8 and 4 respectively. B and C. So we have to sketch the free body diagram, okay, after settlement. Sketch free body diagram after settlement. So original is horizontal. Original is horizontal. Okay, B and C. B settle, C settle. B8, C4. Okay, so this will be the position after settlement. A remain at same position. A remain at same position. Always remember, we have to identify where is the triangular. We have to identify where is the triangular. So for AB, so this one is A, B, and C. Okay, this is 8. This one is 8. 8 mm. This is 4 mm. Okay, so what we get? Okay, find the triangular. Find the triangular. So we mark the triangular. Okay, the triangular. For BC, where is the triangular? Because we have to mark the triangular. This is the triangular. So the triangular for AB, B prime. So this one is B prime, this one is C prime. The first triangular for AB, B prime is triangular. The second triangular for BC, no, it is not B, it is B prime, C prime. And there is one point here. Okay, the triangular that we measure, that we get, okay, after B settle, C also settle, so we get this. This is the triangular. This is the triangular. So we have two triangular. We have triangular number 1 and we have triangular number 2. Okay, so this is 4 meter, this is 6 meter. Okay, For AB, we have this. We have this. Length is 4 meter. Okay, delta is 0.008 meter. This is the perpendicular. It is perpendicular between length and the delta, perpendicular. The angle clockwise. Angle is clockwise. So FEM must be counterclockwise. So the moment will be counterclockwise. So how to calculate this? So this is A, this is B. So we get FEM for AB equal to FEM for BA, and this is equal to the moment we should get negative moment. We should get negative moment, so we put negative and we calculate 6 both and fixed formula is 6 EI 0.008 divide by 4 square. EI is given in the question. 30,000. EI is 30,000. This one, 30,000. So we calculate the value. It is 6 times 30,000 times 0.08 divided by 4 square. It is 16. Divided by 16. So we get negative 900. Negative 900 kilonewton meter. Okay. So this is for AB. So what about BC? Okay, so the green one. The triangular. The length is 6 meter. Okay, this is B and C. Okay, representing triangular for BC. Okay, so the angle is negative. Chord rotation is negative. FEM positive. Okay. So what about the height? The delta. The delta is the difference. This is the delta for BC due to support settlement. The delta is not 8, but the delta is 4 because we only consider the triangular, not the trapezium. We only consider the triangular, not the trapezium. So it is 8 minus 4, so it is 4. So this one is 4. 0.004. Okay. So we calculate FEM. Okay, but before that, okay, the angle is negative, FEM positive. FEM positive because FEM we push back the beam to its original position. Okay, so FEM for BC equal to FEM for CB, this is equal to positive, even though C original is roller, but I choose to solve by considering, assuming both end are fixed. Both end are fixed, so I apply formula for both end fixed or for end fixed. It is 6 EI delta over L. Delta over L. So it is positive because of the behavior. It is positive 6 EI. The delta now is 0.004. L is 6 square. And the answer is positive. Positive. It is 6 times 30,000 times 0.004 divided by 36. It is 20 kilonewton meter. Okay, double check. 6 times 30,000 times 0.008 divided by 16, 90, not 900. Okay, so we get that like this. Okay, this value we have to combine. We have to combine with FEM due to loading. We have to combine. So we can summarize the moment FEM for AB. It is AB just now. AB negative 120. It is negative 120. Negative 120 minus 90. That is for AB. AB. FEM BA. It is positive 120 minus 90. For FEM BC equal to, I think it is the same value, negative 120. Okay, negative 120. Negative 120 plus 20. And FEM CB is positive 120 plus 20. So this we get a negative 210. This one we get 30. We get 30. It is positive 30. FEMBC is we get negative 100 kilonewton meter, and we get 240. This is positive 240 kilonewton meter. Okay, so this will be the FEM combination. FEM due to external loading and FEM due to support settlement. FEM due to support settlement. Okay, so what next? Okay, so in this solution, okay, in this exercise, the solution will be based on the formula of FEM considering end pin or end roller. Okay, I will do another solution. Okay, another one, and we will compare the answer. Okay, compare the answer. Okay, so we have 2 members, 4 member N. 4 member N, so we have A, B, B, A, B, C, C, B. Okay. Okay, we get 0 here, we get 1, and we get 0.667 and 0.333. The FEM, this is distribution factor. The FEM, okay, from this we get negative 210, negative 210, and then we get positive 30, and then negative 100 and positive 240. Okay. Okay, now we will start the first distribution. We will start the first distribution. We will start the first distribution. Distribution number 1. Distribution number 1. Okay. Distribution number 1 for AB, because the factor is 0, so we don't have to do anything. For BABC, okay, BABC, the factor is 0.667 and 0.333. Okay, total moment is negative 30 and 100. That is total moment because it is opposite. Total moment is negative 30 and 100. Total moment times with factor 0.667. We get here is 46.69. 46.69. So it is times 0.333. We get 23.31. Always remember this 4 value, 1, 2, 3, 4. Total must equal to 0. Okay, because total join moment must be equal to 0. Okay, then for CB, the factor is 1. The factor is 1 means that we have to distribute. For AB, we don't have to do anything because of the factor, because it is 210 times 0. But for CB, since the factor is 1, so what we should do is it is negative 240, because negative 240 is joint moment. 240, this 240, okay, this 240 is actually member and moment, and we distribute joint moment, and joint moment is negative 240 times 1. Negative 240 times 1, we get negative 240. Negative 240. Then we move to the next step, that is carry over. Okay, so this is the table, distribution table. Okay, this has two span, this beam has two span. So as I said, for two span, so the process is very short. Okay, the first member end moment in the table, we get from fixed end moment. Okay, we put the total fixed end moment considering both external loading and support settlement. We get 4 values. Okay, including CB because we assume both end are fixed for member BC. Okay, so then we have to start the distribution. So always remember that we distribute joint moment. How to do that? We distribute joint moment. A joint moment we times with the factor. Joint moment, we get joint moment, means that we total the fixed end moment. We change sign because to represent opposite condition.